What's up, everybody? This is section 3 for the final review packet, which is about derivatives. So let's start with question number 8. Question number 8 has us compute the derivatives of the given functions there from the definition. In other words, we have to take the derivative using the limit definition. So let me go ahead and I'm not going to do all of them just because these take a while. See as well, why not?
So let's start with part A. I have to take the derivative of the following function, f of x equals x squared minus 3x plus 1, and well, let's see, the derivative f prime should be the limit of f of x plus h minus f of x all over h, right? So this is as h goes to 0. So let's go ahead and compute that. F of x plus h is going to be x plus h quantity squared minus 3x plus h plus 1. And now f of x is just minus x squared plus 3x minus 1. That's the numerator over h. And I always forget to write my limit sign. So that's what we have so far. And now I just multiply everything out, right? So this is going to be the limit as h goes to 0. What do I get on top? Let's see, I have x squared plus 2xh plus h squared minus 3x minus 3h plus 1 plus minus x squared. Let me fix that. Plus 3x minus 1. So let's cancel what we can. I'll start with the constants. They go away. The x squares go away. Also the, of course, this is all divided by h. And also the 3x term goes away, just like so. So I'm left with something that all has an h in it, which means I can factor out an h. So now this is the limit as h goes to 0 of, let's factor out an h. I'm left with 2x plus h minus 3. Okay, and this is all divided by h. So now, once I cancel the h's, I take the limit as h goes to 0, so I end up with just 2x minus 3, which is exactly what we would expect to get for the derivative of that function. So let's do one more, right? This one was fairly simple. It was just a polynomial. Let's look at part B, which has the function g of x equals square root of x. So the technique for that, of course, we're going to have to end up using the conjugate, right? So g prime of x is the limit as h goes to 0 of, well, I have root of x plus h minus root x all over h, and now I have to multiply by the conjugate. So I multiply by root x plus h plus root x divided by the same thing. And when I multiply the numerators, I end up with the limit. Let's see what we get. It's this squared, so x plus h minus that, right? All divided by h times the quantity root x plus h plus root x. So this is, once I cancel the x's and once I cancel the h's, it's the limit as h goes to 0 of 1 over root x plus h plus root x. So now I can just plug in 0 for h, so I get 1 over 2 root x, which is exactly what the derivative of the square root function should be, not just, from the power rule that we're used to using. Okay, and actually I think I'll stop here. The other ones are fairly similar, and so there's not a whole lot going on here, right? I'll move on to the other problems just because this particular section has a lot of problems, so I don't want to spend too much time on the more elementary stuff. I want to get to the deeper questions. So let's look at problem 9. Problem 9 has us just find tangent lines, and I'll do part
b as an example, right? So I'm looking at g of x, which is ln of 2x plus e, and I want minus 1, and I want the tangent line at the point 0, comma 0, right? So of course, to find the equation of a tangent line, the thing that I need to do is I need to take the derivative first so that I can get my slope. So the derivative here is 1 over 2x plus e times 2, and when I evaluate that at x equals 0, which is the x-coordinate of my given point, that's 0 over there, I just plug in 0 for x, so I get 2 over e for my slope, which means finally that the equation of the tangent line is going to be y minus 0 equals 2 over e times x minus 0. And of course you can simplify that to say y is equal to 2 over e x, and that's the answer there, right? For the other two problems, the process is similar. We're given the function, we're given the point, take the derivative, find your slope using the x-coordinate of the point, then write the equation of the line, and you're done, right? So these are fairly straightforward problems. I don't want to spend too much time on that. But let's move on to problem 10, right, which is a little bit more involved. So problem 10 has us find some constants a, b, c, and d such that the following piecewise function is differentiable. So the piecewise function given here is f of x is equal to, and I have x squared plus x plus 1 for, on the interval minus infinity to minus 1. I have ax cubed plus bx squared plus cx plus d on the interval closed at minus 1, 0, and I have e to the x minus 1 on the interval, let's see, 0, infinity. Okay, first, in order to have differentiability, we need continuity, so we're going to take continuity first. And at the point x equals minus 1, we look at the limit from the left, right? So when I plug in minus 1 in the limit from the left, I get minus 1 squared plus negative 1 plus 1 should equal to the limit from the right of this, right, which invokes this polynomial. So it's negative a plus b minus c plus d, right, when I plug in negative 1. So let's see. This is positive, that's negative, these cancel. So I have the equation minus a plus b minus c plus d equal 1. I get one equation involving the 4 variables. I do the same thing for x equals 0. Wait, what did I write? I switched the... So at x equals 0, again I want to look at continuity, so plugging 0 for x, on the left hand side, or the continuity from the left, I just get the d equals, right, because all of these terms that have an x in it drop, and it should be e to the 0, which is 1 minus 1, so d is 0, right? So the equation that I get is d equals 0, which immediately helps me solve for one of the variables, luckily. So now I need differentiability. And what I'm going to do is I'll take the derivative of each branch of the function and create the piecewise derivative, right? So for the top I have 2x plus 1 for the derivative of the top, and that's on the interval minus infinity to minus 1. And I'm going to make it open because I don't know yet that I have differentiability at 1. Then I have 3ax squared plus 2bx plus c for the middle part, and that's from minus 1 to 0. Again, I make it an open interval because I haven't established differentiability at the point minus 1 yet. And last one is just e to the x on the interval from 0 to infinity, right? So that's
the derivative, the piecewise derivative of my original function. And in order for the function to be, in order for the original function f to be not continuous, to be differentiable, I need my derivative to be continuous, right? So now I need continuity of the differentiability of the derivative. So let's see, what do I get? At x equals -1, I look at the top branch, I have -2 plus 1 should equal to, I plug in -1, so I just get 3a minus 2b plus c. So the equation that I obtain from here is 3a minus 2b plus c equals -1. And then for the other point at x equal 0, I immediately get that c is equal to 1. Perfect. So what do I have? I've just obtained 4 equations with 4 unknowns. So this is a system of equations, and I just solve, right? I'm able to determine the solution. So let's see what we have. D was 0, C was 1. So those are done. I just have to solve for A and B. So what I'll do is I'll take the top equation, minus A plus B. C is 1, so -1 equals 1. And then the other equation from here, I have 3A minus 2B. C was 1, so plus 1 equals -1. Okay, D was 0. So now I'm looking at the following system with 2 unknowns. So let me see, what's the best approach here? Of course, I want to move all the constants to one side. So I'm looking now at the system minus A, and I'll multiply the top equation by 2. So minus 2A plus 2B I move the 1 to the other side, so this all equals 2, but multiplied by 2 it should be equal to 4. And let's take a look. The bottom one is 3A minus 2B should equal to -2. So now I add the 2 equations so that I eliminate the variable B, and I'm left with simply A equals +2, which means that B is equal to, let's see, B is 2 plus A, so B should be equal to 4. And that's it, you know. And let's double check. -2 plus 4 minus 1 equals 1. It does indeed work. So I just solved for all the variables. A is 2, B is 4, C was 1, D was 0. Those are the values of A, B, C, and D that make my function differentiable. And that's the end of that problem. So let's move on to problem 11. So let's see, what do we have for number 11? One second, my phone is bugging me right now. I have to put it on silent. Okay, number 11. I have to show that there's no A, B, and C that make the following function differentiable. So I have cosine of -2x on the interval -infinity to -π/4. Okay. Then I have ax squared plus bx plus c on the interval -π/4 to 1, +1. And then I have natural log of x on the interval 1 infinity. And I guess this is a square bracket and that's a square bracket. There we go. So I have to show that no such A, B, and C exist that make this function differentiable. And just like in the previous problem, first I need to establish continuity. of my function, right? Before I have differentiability, I have to have continuity. So at x equals minus pi over 4, what do I get? Well, cosine of minus pi over 4, well, I have to plug in that into cosine of minus 2x. So I have cosine of positive pi over 2, well, that's 0, should be equal to a times the quantity pi over 4 squared plus b times the quantity minus pi over 4. Here I dropped the minus sign because it's squared anyways and I just don't feel like writing it, plus c. Right, so I get one equation involving a, b, c. At x equals 1, which is the other point in question, right, where we have a jump in the definition of our function. Let's see what happens. I have a plus b plus c equal to ln of 1, which is 0. Excellent. Alright, so let's see now. That's continuity. That gives me two equations. Let's also take the derivative, right? So let's move on to differentiability. So I need to take the piecewise derivative of f, which is f prime. Well, I have the derivative of cosine, that's going to be negative sine of minus 2x, but the negative 2 comes out, so it's just twice sine 2x, right? Negative times a negative is a positive, and this is from minus infinity to minus pi over 4. Then for the second part, I have 2a plus b on the interval minus pi over 4 to 1. And lastly, I have 1 over x on the interval 1 to infinity. And again, I make these open intervals because I haven't established differentiability at the jump points yet. We'll do that in a second. Okay, so now I have to look at the continuity of f prime. So I look at x equals to, let's see, what was it? Minus pi over 4. I plug into here. Cosine of negative pi over 2 is, let me see. Oh, I see what's going on. Okay, so minus pi over 4, this becomes sine of pi over 2, right, which is 1. So on one hand, I have 2 equals to, and I just plug in, and I got the wrong derivative. Derivative should have been 2ax here for that. I plug in negative pi over 4 into that equation here. So I have 2 canceling the 4, so I have minus a pi over 2 plus b, right? So if I rewrite this, I have minus pi over 2a plus b equal 2. So that's one equation. And now at x equals 1, which is the easier point to compute, I simply have 2a plus b equal to 1. Okay, so that's the other equation. So now let's take a look. Now I have two equations, two variables here, which means I can solve for a and b. Right, so let's multiply one of the equations by a minus sign. I'll multiply the top one so that I make this variable positive, and I'll write it one below the other. So I have pi over 2a minus b equals negative 2, and I have 2a plus b. Let's add the two equations together and see what happens. The b's disappear, so I'm left with simply just pi over 2a, pi over 2 plus 1, so plus 2 over 2 times a equal minus 1. Okay, let's add the fraction together. This means a times the quantity pi plus 2 all over 2 equal minus 1, and I hope I haven't missed anything. I remember doing this yesterday in the review session, and I think I got something with a 4 there, but let's hope this works out okay. Let's see. And that means that a is equal to, let's see, oh, of course, this is 4 over 2, that's why, yeah. So this is pi plus 4 divided by 2, yes. So that means a is equal to minus 2 divided by this, right? So I multiply by the reciprocal, which is just negative 4 divided by pi plus 4. And I hope I didn't miss any negative. The signs look okay. So that's the value of a, and now I'm able to solve for b, because b is equal to 1 minus 2a, so it's 1 plus twice this amount now. So it's going to be 8 over pi plus 4. I'm not getting the same thing that I got. Let me just double check the algebra here. I must have messed something up. With the signs somewhere. Well, anyways, let's see what comes out of this. So this is pi plus 4 plus 8 divided by pi plus 4. So this is just pi plus 12 divided by pi plus 4. That's the value of b. So that's a, that's b. And let me just double check on my phone, because I took some pictures yesterday when I was solving this. So a turned out to be, let me see, oh, of course, this is minus 1. I don't know where I got this 2 from, this extra 2 from, so this should have been, yeah, this is my mistake right here. This is minus 1 times the 2, and so a should be just minus 4 over that. So b is this now. Let me see. Yeah, a is minus 2 over pi plus 4. b is 1 minus 2a, so it's 1 plus 4 over pi plus 4, which makes it pi plus 8 over pi plus 4. So let me just recap. Let me write these down here. A was negative 2 over pi plus 4. B was pi plus 8 over pi plus 4. Right, just messing up on the algebra here. Okay, great. So I have the values of a and b. Now what I want to do is I want to go back to these top equations and plug in those values. And ideally what will happen is I'll get some kind of contradiction. So let's see, I plug in something for a in the top equation. I get minus 2 over pi plus 4 times pi squared over 16 plus b is pi plus 8 over pi plus 4 times negative pi over 4, and this should all be equal to negative c, right, if I move c to the other side of the equation. And then I move c in this one, so a plus b should also be equal to negative c. So I have minus 2 over pi plus 4 plus pi plus 8 over pi plus 4. And now if I add all this together, I get pi plus 6 over pi plus 4. So on one end I have pi plus 6 over pi plus 4. On the other hand I have this ugly expression over here. But notice that the left hand side is negative, right? Because these are all positive quantities and they all have a negative sign attached to them here and here. Whereas the right hand side is definitely a positive number. So no such value of C exists, right? It's impossible to find C that satisfies both of these, where one of them is negative, the other one is positive. So that's why this one, you can't find an example of that is differentiable. Okay, so let's see. That's done. That's problem 11. Let me take a look at problem 12 now. So problem 12 has us give an example of a function that is not differentiable because of a cosp, and the other one that is not differentiable because of a vertical tangent line. So for the cosp part, basically what that should look like is it should still be continuous, but it should have a sharp corner like that, right? And let me think, how can we do that? One way I can think of doing it is simply I can take a function like this, which is something like the square root of x, and I can take its mirror image, so then I obtain a cosp over there. Okay, so one way to do this is, let's just say I take the square root of x plus 1. Okay? Square root of x plus 1, what that function is going to look like is it's going to shift the square root of x function to the left 1 unit, so it looks like this. But now I want to restrict the domain, right? So I want only x to be greater than 0. And the way I can achieve that is by making, right, to get rid of this piece, I can, for example, do the following: square root of x plus 1, just like so. Another way to do this, and I think a better way to do this, I can say take the square root of the absolute value of x plus 1. So now what this is going to look like is I simply have the following, right? The square root of x plus 1 looks like this. Absolute value of x is always greater than 0. So for the square root of x plus 1, I only take this portion, but it's going to be symmetric about the y-axis because of this absolute value sign, right? So whatever positive value for x I plug in, I get the same result when I plug in the negative value. So this here is one example of a function that has a cusp and it fails to be differentiable at that sharp corner over there. Okay, now what about a vertical tangent line? Well, I kind of already had something going on here, right? So for the vertical tangent, what I can look at, for example, is the cubic root function, right? Cube root of x. What that looks like is like this, right? And at x equals 0, it's going to have a vertical tangent line, right? And I'll try to draw it in like this with color. That green line, although I don't know if it's visible on the video, that is a vertical tangent line. Okay, so how do I show this? The derivative of this is going to be 1/3 1 over x to the 2/3, and notice it's not defined at x equals 0, right? So it's not differentiable at 0. And there you go, that's an example of a function that fails to be differentiable because of a vertical tangent line. Okay, so I'll stop the video now and I'll continue with part 2 for the remaining of the video, just because I don't want to make these too long. So let's see.